All right, so this is page 400, number 1. Hopefully the classifying part was pretty easy, okay? Point A was a max, point C is a min, and what is point B again?
Plateau point.
Point B is a plateau point, okay? Plateau point. All right, plateau point. Now, really what that indicates, guys, is it indicates a situation where typically that'll come from when we're finding those critical values, but we get one that's a double root, okay? So like, we don't have the original function for this, but there's a critical value here. The tangent line technically is right there. It levels off for just a moment. And you're like, well, that's not a tangent. It goes through the graph. The slope is actually 0, right at 0 here. Okay? But that usually happens because our derivative has a double root in there. Okay, but let's consider part B here. We have a sign diagram. The critical values for this, if this is the original function, what are the critical values?
-2, 0.
Okay, anywhere you see a max or min point or a plateau point, that came from a critical value. And now, let's think about, we're kind of doing this a little bit backwards because we can see where it's increasing and decreasing, right? So, we know that the derivative is going to be what? Positive or negative to the left of -2? It's positive because we're increasing. All right? So we have a positive derivative. From -2 to 0, our derivative is negative. From 0 to 3, it's negative, okay? And then from 3 to infinity, it's positive, okay? So what we would say here is that we are increasing. All right, so look at part C. We're increasing from -infinity up to -2, and from 3 up to positive infinity. Okay?
Sorry, how did you get -2 again? Just because it's the derivative?
Just because we know that
Oh,
critical
they
points
gave them.
are, yeah, they gave us the max and min points here, so. Okay. And then we also know we're decreasing from -2 to 0. And we're also decreasing from 0 to 3.
So you stop with the or graph.
Okay? Now, I wrote it as 2 separate ones so that I remember 0 is a critical value. Because technically, when you're at 0, you're not doing either.
Is
Okay?
it a plateau?
But we still, yeah, it's a plateau right there.
Wouldn't it be an open interval on 0 then? For both?
You don't, here's the thing. There's a distinction that you guys will make in the AP that we don't make here. And that was in the video, was the strictly increasing versus just increasing.
Yeah.
And if we're talking, and what you would do is you would use open intervals. They don't care if you use open or closed intervals, okay?
But if I use open, it won't dot com.
No. So, right, because technically, yeah, it's 0 at the critical value, so it's not technically increasing right at that moment. So, all right, so we have this, and then This part D is actually easier than it may seem. It said draw a sign diagram for f of x for all x's, okay? So I want to do another sign diagram. The question is, what numbers am I going to put on my number line here for a sign diagram for the original function?
Yes.
What are you talking about?
So that for the original's graphed, and to get those answers, we took the derivative of the original.
Okay, we took the derivative of the original, and where did these numbers come from?
The x value.
The x values when the derivative
0.
is 0, okay? So, for the original function, what numbers are we going to put on here?
I don't understand. Where is the derivative on the graph?
It's nowhere, it's not up there.
So what do we take the derivative of?
We didn't take the derivative of anything, we inferred things about the derivative by looking at the original function. Okay?
This is the derivative.
Right.
The derivative is the slope at point of tangency, right?
Yeah,
So,
but we're talking in general, we're not looking at a specific point here.
yeah, because I don't understand what, like, I can't conceptualize it when you're talking about derivatives, it's that whole thing is so smoothly.
It's the derivative of the function. So you know you can get the derivative of a point, you can get the function to get the derivative at every point. That's what that.
And it's of that.
Yeah.
Yeah.
F prime is derivative at any given x.
Why do we care about the derivative?
So it tells you how fast.
Because that's, the derivative tells us our rate of change at any moment. So the derivative is going to equal something different here than it does here, or that it does here. They equal a different value at specific points, but the same derivative function will give us the value of that derivative at any point. Okay, that's what he's saying there, okay? What I'm trying to get at though here though is something different. You're talking a much bigger picture you need to come for some extra help about. I can explain that. That's a big question that you just asked that needs answered, but not at the moment, okay? How did we get these numbers? I know how we got them just by looking now, but how do we normally get these critical values? It's when the derivative
0.
is 0, okay? So if we're going to do a sign diagram for the original function, then the numbers we're going to put on here are going to be when
X is 0.
when not x is 0, but the original function is 0. When is the original function 0?
-4, 5, and 0.
At -4, at 5, and at 0. Okay?
So that's when all the Y's are?
Helps if I put them in order.
Yeah.
0, 5. Okay? So we're doing a sign diagram, okay? And notice here, what we're talking about, guys, is here, we're really doing the same thing with two different functions, okay? But the interpretation in the end is different. Here, the values on the line are where it equals 0, and then here it tells us if it's positive or negative. Okay? So this is where f of x equals 0. Is f of x positive to the left of -4 or negative?
Negative.
It's negative because it's below the x-axis, so it's negative. How about here?
Positive.
It's positive between -4 and 0. Between 0 and 5, it's negative. And then here, it's
Positive.
positive. Okay? So, here's the thing. I'm doing the same thing, but the way I will interpret and what this tells me are two different things. Okay? Some of you need to stay with me here because you're going to be totally lost. All right? Focus, please. Here, the positives and negatives tell me how my graph is changing. I'm increasing here, I'm decreasing here, I'm decreasing here, I'm increasing here. With this sign diagram, the positives and negatives tell me something about my location. Okay?
Sign, not like the trig function.
Yeah, not the trig function, the sign. Okay? So here, this negative is not telling me anything about increasing or decreasing because f of x doesn't talk about increasing or decreasing. F of x is telling me about my position. So here, I am below the x-axis. Here I am above. I'm below here, and I'm above here. Okay? Hey guys, this is something that you have to do when we're talking about derivatives. You've got to understand what we're dealing with, and this happens a lot where we're doing the same thing with the derivative that we would do with the original function. So the processes are the same, it's just a different way of applying the same thing. Okay? Now, let me show you how this can be used. Okay? I'm going to give you a graph here, but it's not going to be the graph of a function. It's going to be, or of the original function, it's going to be the graph of a derivative of a function. Okay? So let's say I have this function here, and I've got this. Okay? And let's say this is negative 5, 0. This is 1, 0, and let's say this is 4, 0. Okay? But this is f prime of x. Okay? Now let's analyze this graph and see what we can figure out about the original function. Okay? First of all, we can see our critical values of the original function, because the critical values of the original function are where the derivative is 0. So our critical values are what? Negative 5, 1, and 4. Okay?
So this just means
So those are the critical values, but then, can you go up for a second? But then on that graph, the critical values were the y.
Because this is the graph of the original function. They were still the x-coordinates, but they were taking them from the original function, and that actually tells us those values we see down there are going to give us max min points or plateau points. Okay? Here, to the left of negative 5, my derivative is negative, which means the original function is going to be doing what? Decreasing. Okay? F of x is going to be decreasing. All right? Between negative 5 and 1, my derivative is positive, so my original function will be increasing. Okay? Between 1 and 4, my derivative is negative, so the original function is decreasing. Okay? Yeah.
For what you're doing there, why is that f prime of x if it's where the actual function equals 0?
It's not. This is f prime of x. We're going backwards now.
Okay, I didn't see that.
Yeah, we're going backwards here. If we're given the derivative, we actually can come up with a pretty good view of what the original function would look like. Okay? And then after 4, notice the derivative is positive again, so I know that we are increasing. Okay? So let's think about this. What I now can see is, hey, I changed from decreasing to increasing at negative 5. What does that mean happens at negative 5 on my original function?
it's a min-max or
It's a minimum. If I was decreasing, and now I'm increasing, I have a min point here. Okay? So I'm not exactly sure how high or low it is because I don't have an exact function, but let's say it's here. Okay? I know that my function is going to come down and hit a minimum there. Oh, no, not f prime. This is going to be my f of x. All right? Then I'm going to increase until I get to 1 and then start decreasing again. So that means at 1 I have a max point. All right? So let's say it's up here. So now I'm increasing. It's going to hit this and it's going to start coming down again. All right? And then what do I have here at 4? Another min point. Okay? So let's say I don't actually cross the x-axis. It doesn't have to. Let's say it just comes down to here now. It hits that min and then it starts going up. Okay? Notice we're increasing once we get past 4 again. So that is something that my original function might look like. Okay? I can at least get an idea for the general shape of my original function if I look at the sign diagram of the derivative. Okay? Now, let me go back here a moment, and let's actually kind of do the opposite here, using what we know with this original function, okay?
Wait, I don't understand how you took the where y equals 0, where the derivative is 0, you have -4, 0, and 5. You took them and you
Wait,
put them on
are
a
you
graph.
looking down here?
Yeah,
Okay.
and then when you put them on a graph by themselves, you did the function, but that function doesn't look anything like the one on top.
Well, these are two different problems.
But you use the same, you use negative.
Oh, I just picked -5, 1, and 4. I just picked random numbers.
Okay.
Okay. And I just sketched a random graph to kind of illustrate how we can work backwards. You know, or we can, and this is what I was going to do, and then I'll get your question here. Using what we know now, anywhere we had a max or a min point or a plateau point, if I were sketching the graph of f prime, at -2, f prime would cross the x-axis. And here at 0, it would cross the x-axis again. And here at 3, I would hit the x-axis again. Okay? And then over here, if I use my sign diagram, my derivative is positive, and then it goes to negative. So it goes through this. See here, the derivative is positive, and now it's negative. It goes from positive to negative when we switch from increasing to decreasing on the original function. Okay, because here my rate of change is positive, increasing. Now it's negative, I'm going downhill. Okay? So my derivative is negative until I get to 0, but notice it stays negative. Or it goes back to negative. So I must have a double root there at 0. I come up and just touch it, but then it starts decreasing again. That's what happened here. It was decreasing. It paused for a moment at 0. So I had that plateau point, and then it continued to decrease. So my derivative stayed negative. And then after 3, my derivative was positive again. So here, positive, I'm above the x-axis. Okay? So here's the graph of the original function in green. This would be the graph of my derivative function in blue. And you'll notice the critical values on the original function become the zeros of the derivative function. Okay? The increasing becomes parts of the derivative function that are above the x-axis, The intervals that are decreasing on the original function are the intervals where we're below the x-axis on our derivative. Okay? So, Sammy, what was your question?
What would it look like on a sine graph if you had a plateau point instead of a max point?
It actually looks right like this.
So where two are two consecutive sines that are the same.
Exactly. Right here, see it goes from increasing to decreasing, that's a max. If it is doing the same thing on both sides of a critical value, that's a plateau. Okay?
But I thought a plateau point was where I thought that, never mind. So it's just where it's the same. And that's a double root, always, or just because of that one?
It happened to be, in this case, it was a double root. A lot of times, I would say most of the time when you've got a plateau, it's because there was a double root there in your derivative.
Okay.
Okay? Yes?
So, what I don't understand is like, if you can have a derivative function, and you can take, and then you can plug points in, and you'll find like the derivative at that point.
Yes.
But what is that big f prime of x like function there? Like, that's our derivative function?
Yeah, that's your derivative function, okay, that allows you to, it's just in general, it's kind of like having, the formula for a circle, the area of a circle is pi r squared. That's in general what the area is, okay? But when you want to find the area when the radius is 5, you plug in a 5. Or when you want to use the area when the radius is 7, you plug in a 7.
But I just don't understand how like,
It's basically every function has its own unique formula for the rate of change, and that formula is our derivative function.
We take the original function, do the powers and stuff to get that derivative function, and that's the function.
and why did all the critical value points become our zeros?
Because that's the definition of what a critical value is. It's when the slope of your tangent line equals 0. The slope of that tangent line right here is 0. So when I'm graphing my derivative is rate of change, it is slope, so it has to be hitting 0. Okay? So, I do want you to be able to be able to see a graph. Look at a graph, and if you're told that's the derivative function, you should be able to pick out some things about an original graph. Let's do another one here. Let's say that I just have this, okay? I'm going through the point 2, 0, and I just have a line. Okay? I've got a line. But that's my f prime. Okay? Here, f prime equals 0. So that means at 2, my original function has either a max or a min point or a plateau point. Okay? Yeah, it is. Okay? Because f prime of 2 equals 0, that means that f of x has a max, min, or possibly, or a plateau at x equals 2. Okay? That's what it's telling me. All right? Now, I can tell if I look at a sign diagram for f of x, I'm only going to have one number on that sign diagram. I'm going to have 2. And f prime, to the left, f prime is well, f prime is negative, okay? And to the right, f prime is positive. And that means f of x, the original function, is decreasing and increasing there, okay? Be careful, don't just say, oh, f prime is decreasing. No, actually, f prime is increasing the whole way here, okay? We're talking about what the original function is doing as a result of the sign of the derivative. Okay? So, using that, then, we're actually able to sketch our graph. Okay? I know that I'm going to have a min point at 2. Okay? And I'm going to be decreasing coming down to it, and I'm going to be increasing after I pass it. And guess what? We have a parabola here. Now, that parabola, without more information, I don't know exactly how high that parabola is. It could be anywhere as long as the minimum value is when x equals 2. That vertex could be 2, -3, or it could be 2, 4, or, you know what, it could be 2, 0. We don't know because we don't have any more information on this one. But we can at least tell this much. We know it's a parabola, and it's going to have a min point. Okay? Now, all of this brings us actually to, it actually brings us to another thing here that I want to look at, and that is, how do we prove that something is a min point or a max point? All right? Let's say we're told that there's something that is a critical value, and we're asked to show that this is a min point, or show that this is a max point, okay? Let's do a kind of a simple example here. Suppose we had the function f of x equals an x squared plus, let me do 8x plus 12, okay? And I want you to prove to me, that the point -4 is a min point.
Is that where the derivative is 0? Is that?
Okay? So, here's the deal. We've got 2 steps to this. If you're asked to prove that something is a max or a min point, which was either on last year's exam or the year before, they had one exactly like this, okay? There are 2 things that you need to do. First of all, you need to prove that this value of x, -4, is a critical value. Okay? So the first thing is it a critical value? Well, if it is, then f prime of -4 would have to equal 0. All right? So does f prime of -4 equal 0? That's the first question. So, what's f prime?
2x.
Come on, guys. What's f prime?
2x plus 8.
Okay? 2x plus 8. All right? And if I plug in -4, 2 times -4 plus 8 equals -8 plus 8 is 0. So, yes. Okay?
Why does 7 equal 0? derivatives are minimum.
Because a min point always occurs at a critical value, and critical values are where what happens?
Where the
The derivative has to equal 0, okay?
oh, is that prime?
Yeah, f prime. All right, so then the second thing, you have two options of how you want to do this. Once you know for a fact it's a critical value at -4, then you have to do one of two things. The second one we don't know how to do yet. Notice it's f double prime. That's a second derivative. Okay, that just means we took the derivative of the derivative. All right, we'll do that later. It's not as hard as it sounds. All you have to do is prove that it's either, wait, I mixed those up. It's positive, in which case you would have a min, whoops, or negative, in which case you would have a max. All right? But we're not going to do that here. The other way you could do this, though, is to show that there is a change of sign in the derivative, okay? So for that, we want a sign diagram, or for f prime of x. So we need to think in terms of, when does our derivative equal 0? Well, it actually only does in one spot, right? It only happens at -4. You know, if you set your derivative equal to 0 and actually solved it, -4 is the only answer you would have got. Okay? Now it's possible that it could be -4 and something else. Okay? But in this case, we only have the 1, and to the left of -4, if I plug in, say, a -5, is f prime positive or negative? Negative, okay? -10 plus 8 is -2, so I know it's negative here, so I know my original function is going to be decreasing. Okay? If I plug in 0 or anything else to the right of -4, let's plug in 0, we get positive 8, right? So I know it's positive, which means my original function is going to be increasing. So do we have a minimum point? Yes. That's the other thing. Make sure that if they ask if it's a min, it's not accidentally a max. All right? To be a min, it's going to change from going down to going up, from decreasing to increasing. So yes, we do have a minimum point at -4, -4. Okay? And we did it by proving that we're changing sign at -4. Okay?
For finding like whether it's positive or negative, can you just look at the derivative function? Just look at like whether there's no leading coefficients positive and stuff like that.
Well, that would tell you the far right side. You could use your leading coefficient test and the degree of it if it's a polynomial. Yeah, this one, it's a positive leading coefficient, so we know it's going to be increasing to the right, and the degree is 1, which is odd, so it's going to do something different on the left. So it's increasing on the right, it's going to be decreasing on the left.
Yeah.
In this case, that works. Yeah. So however you figure out to do it is fine. But,
Is cosine of pi over 2 0?
yeah. All right, any other questions? All right. Make sure you're taking the time to work through the practice, okay? It makes me nervous for you when we have this many questions in class, but we had 0 questions about the practice you were supposed to do for today, okay? So I know you guys are busy, but you've got to do the practice. This is the kind of thing you fall behind and you're going to stay behind for a while unless you really, really get moving, okay? So make sure you're doing the practice. Now, I want to do one other thing here. We haven't looked at sign diagrams when there are limitations in the domain of our problem. Okay? This is actually a really good problem because it addresses a few different things. Now, we're not going to go into sketching graphs as much in depth as, say, the AP would. Okay, that's not the emphasis because we're looking at a very practical approach, a problem-solving approach to calculus here. We will do some of it here because I want you guys to see how all this relates. All right, so we have this function, f of x equals x cubed plus 3x squared minus 4x minus 12. And I want to see what we can tell, first of all, about this function without actually doing the derivative or anything yet. Okay? So, just looking at this and thinking back to what you know about rational functions, what are some things that you can see happen?
Difference of squares in the
Okay, we've got the difference of squares in the denominator. We could factor that. All right? And once we have it factored, we can see something about the function. What do we see? Okay, we have either asymptotes or holes. And either way, we've got a domain that's limited, right? So our domain is x cannot be what? Yeah, plus or minus 3. Now, I know we said we weren't dealing with the derivative yet, but one thing that we are going to do is any points of discontinuity, a hole or an asymptote, is going to go on our graph. So we have -3 and 3. They're going to go on our sign diagram, I should say, not our graph. Now, can you guys see what we can do with the numerator here?
Factor everything.
Yeah, let's factor by grouping, okay? Okay. Let's factor this by grouping. We've got an x squared times x plus 3. We factor out a -4 here. We've got an x plus 3, which is really convenient because now look, we've got a common factor of x plus 3. And we got an x squared minus 4. Okay? And what do you see now?
X squared minus 4 over x minus 3.
Yeah, look, this cancels here, which tells us that at -3 we have a hole, okay? We have a hole at -3, and if we plug in -3 up here, we have a 9 minus 4 is 5 over a -6, so -5/6 is where that hole is going to be. But now we have our function that's actually a little simpler to work with. That's x squared minus 4 over x minus 3.
How did you get the 3 and 5/6?
Remember, if you have a hole, if this cancels out, then you plug in that value -3 into what's left over. So 9 minus 4, -3 minus 3. Is everyone with me so far? Okay. So, by the way, since -3 is a hole, because it canceled, what do we get when we have x equals 3? It's a vertical asymptote, okay? X equals 3 is a vertical asymptote. done anything yet with the derivative. This is all just honors pre-cal stuff from last year, all right? Maybe a little rusty, but that's all it is. I'm going to actually start our graph here with what we know already. We know that at -3, here's -1, so at -3, -5, 6, I actually have a hole. So I'm going to put a little open point there. And at +3, I know I have an asymptote. Okay? Now you may notice too that this is an x cubed in the numerator, this is an x squared. When it's bigger on top but only by 1, what do we have? No? Remember Bobo Button?
0.
Okay? For horizontal asymptotes, bigger on bottom is 0. So bigger on top, we have no horizontal asymptotes, but when it's bigger on top by only 1, what do we have? We actually have a slant asymptote. You remember that?
That's not something.
Okay. All right.
I mean, it kind of makes sense on a slant.
Yeah. I'm not going to have you find it right now, but just making connections, bringing things back to memory, okay?
Did we learn that last year? No.
Yep, we did. Chapter 3.
Chapter 3.
Chapter 3 last year.
Mr. Hickson.
All right, so
Remember chapter 3?
It was a long time ago.
42.
No.
The third
all right,
paragraph.
listen up, please. So now we need. We're going to have a sign diagram. Again, we're still going to have -3 and +3 on here, but let's look at the derivative now to figure out any other critical values. Okay, so f prime of x. You can use the reduced one.
We use the quotient.
We will use the quotient rule, okay? We will use the quotient rule as x squared minus 4 over x minus 3. So u is x squared minus 4, v was x minus 3, okay? Let me move this
So
to the side here, okay? So what is u prime?
2x.
2x. What's v prime? 1. All right, so this one isn't going to be too hard at all. We have u prime
2x times x minus 3 minus 2x squared minus 4 times 1
times 1, good.
over x squared minus 9 to the square? Oh, x
Well,
to
this
the
v,
3.
the new v, x minus 3 squared, okay? So that's our derivative. We can simplify it a little bit. It's a 2x squared minus an x squared, which is just an x squared. We have a minus 6x. And we have a plus 4. Okay, and that's over x minus 3. Don't ever FOIL the denominator here.
Should you back to the top?
If you can, because what do we want to do with this derivative? We want critical values, so
0.
set it equal to 0. All right? So what's the only way we get a fraction equal to 0?
The numerator is 0.
The numerator's got to equal 0, so we can ignore the denominator at this point. And our numerator is just a quadratic that doesn't factor, so we've got to use our quadratic formula, right? So our critical values are going to be when x equals 6 plus or minus the square root of 36 minus 4 times 1 times 4, so minus 16, all over 2. That's a square root of 20, which is 2 root 5. 6 plus or minus 2 root 5. I know you guys know how to do this.
I know
Okay.
the song.
So 3 plus or minus root 5.
Wow.
Okay? Now,
Why-
for our
why-
purposes,
It's not plus or minus 2.
well, I canceled out the 2's from the 6 and the 2 and the 2. Got to cancel it out from both of these.
So the critical values are 3 plus or minus root 5.
Yeah, and that's about 2.2. So we know our critical values are 5.2 or 0.8. Okay? Because root 5 is about 2.2. Okay? So guess what? Up here now, we have these other values to consider. We have 0.8. And notice now we have more regions. We have 1, 2, 3, 4, 5 different regions that we need to consider and test. All right? So, let's 1, 2, 3, 4, 5. We got 5 different regions. Okay? So basically, you just need to pick a number in that region, whatever you want. Let me show you kind of the easy way of doing this, because this can get really, really tedious, all right, if you don't know how to use your technology. Okay? If you do know how to use your technology, then this really isn't hard at all right? Our function, we need to test when f prime is positive or negative, right? In those different regions. So f prime is this x squared minus 6x plus 4 over x minus 3 squared. We do need the denominator here, okay? So what I'm going to do is I'm going to try negative 4 first, okay? So rather than punching in, parentheses, negative 4 squared minus 6 times negative 4 plus 4, enter, divided by, parentheses, negative 4 minus 3 squared, and getting a positive 0.897. Okay, that's not wrong, but now I'm going to have to do the same thing with the next one and the next one and the next one to get all the different intervals. Okay, what I can do instead, though, is use your store. Okay, I want negative 4 to equal x. All right, and instead of typing all of that in every time, what I'm going to do is type it in once with x. X squared minus 6x plus 4, close the parentheses, divided by parentheses, x minus 3 squared. And now I know that when x is negative 4, my derivative is a positive 0.897. Okay? But then I need to test it in this region. So let's let x be 0, since 0 is in that interval. So I'm just going to do 0 store x. And remember your entry. Okay? Entry. So second entry brings back the last thing I typed in. If I hit second entry again, brings back that derivative I typed in with the x's. And now when I hit enter, it's going to reevaluate it when x is the new value 0. Okay, so it's a positive 0.444 and so on. So I know it's positive here. Okay, now I need to test it somewhere between 0.8 and 3. So let's try 1. 1 store x, enter, second entry, enter. It's a negative 0.25. Okay, it really doesn't matter what the value is as long as we get the sign. Okay, then we need something between 3 and 5, so I'll try 4. 4 store x, second entry. It's negative. And then I need something to the right of 5, so I'll do 6 store x. See how quickly this goes when you're not having to type the same thing over and over again. Okay? This gives you more time to think about the more challenging stuff rather than spending all your time doing this tedious stuff. Learn how to use your calculators. Second entry, positive 0.44, so I know I'm increasing again here. All right, so check this out. I already knew I had a hole here. I knew that as I approach that hole now, I know that my function is increasing. So it's coming from down here, it's increasing, and then it's going to continue to increase until I get over here to 0.8. Now, I'm not sure exactly where that is. I could plug it in and figure out exactly, but for time we won't. We're going to come up here and hit this. That's going to be a what? A max point, because we're changing from increasing to decreasing, so that's a max. All right? Then at 3, we had this vertical asymptote. And I'm going to be decreasing as I go towards 3. And that makes sense, because we know we approach the asymptote and it just goes down to negative infinity. But what happens when you pass an asymptote? That's right, it jumps way up here, okay? So now we're way up here at infinity and we don't have anywhere to go but to decrease until 1, 2, 3, 4, 5, until we get to 5, okay? And we're going to decrease until we get to 5, and then it's going to start going back up again. And by the way, right, there's that horizontal, or that slant asymptote that we were talking about. Okay, so this isn't drawn perfect here. I know this is actually going to approach that slant asymptote, as will, let me erase this a little bit. Okay, so this is actually going to approach this slant asymptote. So we're going to come over here. We'll still hit the max at 0.8, and then it'll go down. All right, so that's kind of what that's going to look like. Okay? Oh, and by the way, where are the zeros of this function? Two and negative 2, right? Because that's x plus 2x minus 2. Well, look at this. There they are, right there and there. Okay? So, all right. So there's a lot you can do with these sign diagrams, with looking at increasing, decreasing, and putting that together with all the stuff you learned last year. Okay, you're able to really get a lot of information about a function without having to have technology tell you all the answers. Okay? So, any questions?